Okay, it's time again. So let's see. Let me get everything open here. Yes, here we go. Chapter 4, which we kind of just started the other day, but not we didn't get very far. So we're basically starting 4 right now. We're completely done with chapters 1, 2, and 3. Now, because of that, that means it's time to start planning for the midterm. So what we'll do here now, because this is an online class, obviously the midterm will be done on a take-home basis. So but before we do that, what I want to do is have a review session. What I'm going to do is put together what I call my sample midterm. And I do this for all my classes. I just haven't finished the one for this one yet. And basically, it's meant to be sort of a preview of what you can expect on the actual midterm. So in other words, it'll be the same types of questions, same difficulty level. And so what, once I posted it, what I think we should do is the next time we meet, we should go over that and make sure everybody understands what we've done up to this point and, do more practicing and just in general prepare for the test, which will be, like I said, on chapters 1, 2, and 3. And of course, the beauty of having this online is that you can do it at home. You can look at your notes. You can watch the recordings again. And you can also ask me questions by email if you're unusually stuck on something or other, or if there's something unclear about the test. And, like I've been giving you a week to get the the assignments done. So, I'll give you at least a week to get this test done as well. It won't be like extremely, extremely long. It'll just cover what we've done. You shouldn't have any trouble knocking it off. It'll be about the same length you would get in a regular in-person class, let's say an hour and a half, 2 hours or so. So we'll go through that. Like I said, soon enough, maybe tomorrow even, I'll have the sample midterm posted. Now, also don't forget, since today's Thursday, you should be finishing up your chapter 3 problem set. I have a lot of them already, but maybe not every single one of them. Yeah, the whole point of it is to yes. No, I'm sorry. I'm working on those too. Yes, don't worry. Everything, you'll have those way before the midterm is actually due. The midterm wouldn't be due till like 2 weeks from tonight at least, because tonight number 3 is due. Yeah, that's right, isn't it? We've already done 1 and 2. It should be number 3 tonight, I think. Now I'm not so sure. No, I'm pretty sure that we've already done 1 and 2. Yeah, tonight should be number 3. Because we just finished 3 the other day. Yeah, well, I think I just was looking at it before. It should be fine. I chose, it's basically most of it is derivatives based on the rules. Yeah, right, exactly. It's based on chapter 3. Didn't I give you one for the first chapter? I don't remember anymore. I'll look it up, but for this week, the one that is based on chapter 3, see, now I'm all confused. I really, let me go look at Moodle. I'm starting to forget myself what assignments we had. I'm pretty sure that we've had one every week, but I'm not sure about anything. So I'm just going to go look. I know something was supposed to be done tonight, but let me just go look. Okay, so there was a chapter 1 problem set. Let's see, let me look at the calendar too. Our first class was on when did we start? I think it was June the 1st, wasn't it? Like I said, now it's starting to feel like we've been doing this forever. No. Okay. So the chapter 2 problem set was based on limits. All right, I'll tell you what. I'm gonna let me just do this one thing. I probably should print this thing out every time we meet. I'm printing out the schedule that I put together. So I don't hear it printing. There it goes. All right, I'll be right back. All right. Well, that was wonderful. It didn't work. The printer has a problem, so I'll just look it up myself. So our first class was on the 6th. Okay. So that we got that out of the way. Let me go look at the calendar. The 6th. Okay, so this is our 3rd week. So if I gave you an assignment on the 9th, that would have been due. Yeah. Okay, I get it. Looks like you're right. Because this is only our 3rd week. If I gave you an assignment on the 9th, Thursday the 9th, that would have been due on the 16th. That would have been chapter 1. And then that's right. Okay, so my fault. You're absolutely right. Number 2 is due tonight. Number 3 would be next week. Okay, so I'm glad you raised that question because I scribbled this down on a piece of paper and I guess I made a mistake. I should have checked the schedule first. So on this, we would have met, our first day was the 6th. So we had 3 sessions. On the 9th, I would have given you the first one, based on chapter 1, due on the 16th. And then the 16th, I would have given you number 2. It was due tonight. And then now that we're completely done with 3, you can do the 3rd one for next Thursday, the 30th. Okay, now we're all set. Let me write that down. Yep. Very good. All right. So anyway, as I was saying, then tonight we'll just carry on with chapter 4. But next week we will do the sample midterm. We're just going to review it. It's not something you're supposed to hand in. No, you didn't miss anything. No, we're good. And unlike a lot of textbooks, what's great about this book is that the chapters we're doing are actually 1 through 6. In others, in a lot of cases, you have to skip around or, there's gaps and, gets confusing. For this book, at least, we're going to do the first 6 chapters and that's it. So we don't have to worry about the sequencing. I kind of like it that way, but you don't get that very often. So anyway, but the sample midterm is not meant to be handed in. It is just for your own practice. If you can do the problems on the sample midterm, you'll have no problem whatsoever with the actual midterm. Okay, and like I said, I'll give you plenty of time to get that done. You can consult with all of your materials, the book, the notes, the recordings, everything you have, you can use to get these done. Now, of course, this is not like a lot of classes involve a lot of memorizing terms and that kind of thing. Not so much here. It's just straight ahead problem solving. So having access to all the material is helpful, but you really do have to understand how to use these techniques in order to do well. So yes, and you're absolutely right about the other question. I'll make sure that by the time you start working on the midterm, I will have corrected the first 3 assignments. Okay, so, and I'll make sure that the timing is good so you have plenty of time to get everything done. Now, with all that being said, there is one twist though. And they were supposed to tell you about this. I guess, I don't know if they made this clear or not, but next week I'll be away. So what I'm going to do is I'm going to record the sessions in advance. So instead of having our normal meetings at 7 o'clock at night, what I'll do is I'll actually post the next 3 lectures on on YouTube, and then you can watch them whenever it's convenient. So I will not be sending out any invitations, but instead I'll send out a reminder, and I'll say, listen, don't forget that this coming week, the week of the 27th, we're not going to be meeting at our normal times. I'll just make the 3 recordings available to you, and you can watch them at your leisure. And then, of course, you can always send me email questions. I'll still have access to the internet, even though I won't be here. And that hasn't changed. But it's just that we won't have our normal meeting at night like this. Okay. So I'll definitely send you out a reminder about this very, very soon, just to make sure that you don't sit there and wonder, where's your invitation? Well, it's not coming this week, because instead, as soon as everything's posted, you can just go ahead and watch it. Okay. So this is one of the good things about being online. I mean, these kind of issues can be resolved, because, no matter what you do in life, you're always going to have conflicts on your schedule. It can't be helped. So this way we can work around it just by having the normal recordings, except, not in real time. That's all. All right. So now, and by the way, a lot of online classes, that's all you get. There's no actual real-time anything. You just watch recordings and that's it. So here, at least, we have mostly in person. I mean, not in person, real time, but not every single week. All right. Well, with all that being done, let's finally get to our work. All right. So we started to do this Tuesday night. And so we're basically looking at applications of derivatives, but we actually are also introducing some new concepts as well. It's not 100% applications, although there are many of them. But there's some very important new ideas in here. And it's actually a very, very long chapter. There's a lot of content here. So it might take a while for us to get through this. But that's not a problem, because we've actually got, I think our last class is the very beginning of August. So we've got at least 5 weeks left to cover this material. So there's no rush. We're actually ahead, if anything. And so I think you'll find these topics to be quite interesting, but some of them are quite, well, let's just say they're a little abstract. Let's put it that way. But once you get some practice with them, you'll see that they're really not that difficult. So this first part about the linear approximations, which we just looked at a little bit the other night, it's important because it's building up to something, some major results. A lot of results in calculus start out with some simple ideas, and then they build up to something more complicated. And so luckily, we do have the ability to graph a lot of these results in both Symbolab, and the book also has a lot of very excellent diagrams. So you can visualize what in the world is going on here, because otherwise it would be very hard to see what this is all about. I think that really the graphs make an enormous difference in helping us understand these concepts. So we started out by noting that for point A on a function, what we can do, and let me just throw in a quick sketch here, is we can approximate the value of a function by describing a tangent line to the function at a given point. So if we had something like this, let's say this is our function, and we're interested in the behavior of the function at this point A. And so we can describe a tangent line here. And what that means then is that we can use the tangent line to figure out what will happen to the function if we change x very slightly. So let's call this point a plus dA or something like that. Actually, no, not a plus, I'm sorry, a plus dx. which indicates A plus a very tiny change in X. So the tangent line can tell us where we should be roughly if X moves from A to A plus dx. Now you can see, it's dx. You can see it is not perfect. It's only an approximation, but as long as the difference between these two is very small, then the approximation should be very good. Okay, the approximation will be quite close as long as we haven't moved too far away from the original point. And for some applications, this is a very useful piece of information. So the best example I can think of is something from finance where, and I don't know if I want to get too involved with this example if you don't have any background in this area, but what happens is that with a bond, which, you know, it's a debt instrument that you can buy, and you buy it because it provides you with a stream of interest payments. The US government issues a lot of bonds every year to cover their deficits. And so the rate of return to the bond is known as the yield. And so it turns out that the relationship between the price of a bond and its yield looks something like this. It's a negative relationship, but it's not a linear relationship. In fact, it's actually convex to the origin. And so what we can do with this technique that I'm showing you is that if the price is here, let's say, $950, the yield is 6%. If yields in the marketplace start to rise, say interest rates start creeping up and the bonds yield rises to 6.1%. Oh my God, I'm making a mess. What I can do with this technique that we're using here is calculate a tangent line and then use that to come up with the approximate change in the price of the bond based on this small change in the yield. So let's say, oh, what did I do? I'm sorry. This is actually not 6.1, it's 5.9, sorry. It's got to be smaller. So the price, let's say, goes up to 9.53. According to this tangent line, now the actual price might move up to 9.53 point, let's say 20 cents, but this gives us a pretty good idea of what could happen to the price of the bond if the interest rate drops by, let's say, 0.1%. And this is done all the time in the bond markets. We use this type of approach to figure out how much a bond's price might change if interest rates rise or fall in the economy. It's a very common practice. And it comes from this setup that we're creating here, where we're creating a tangent line to a function to come up with the approximate change in its value if X moves a small amount. Anyway, so the example we use is right here, f of X equals 1 over X, which looks like this. We've seen it before. It has two asymptotes. The vertical axis and the horizontal axis are both asymptotes. And so imagine, and by the way, so for this technique, we do need the derivative. And so remember that X, 1 over X, is the same thing as X to the minus 1. And then you can apply the power rule. And when you do, you'll end up with minus X to the minus 2 power, which, if you prefer, could be written as negative 1 over X squared. Anyway, so why do we need that? Because remember, based on this, this expression, the equation for the tangent line to this function at any given point looks like this. So you see, we do need the value of f prime of a. Okay, so let me put this in here so we can see it again. And so what we're going to do is assume that a is -2. For whatever reason, we want to know what's happening at -2. So remember, f of x is 1 over x. F prime of x is negative 1 over x squared. Since a is negative 2, f of a is 1 over negative 2. F prime of a is therefore negative 1 over negative 2 squared, negative a fourth. So the slope, this is the slope, by the way. F prime of a is the slope of the tangent line. But what about the equation? Okay, so if you need to know the entire equation, what you can do is when you plug in these numbers, rearrange it algebraically so that it's written in the traditional slope-intercept form. This would, of course, be our intercept. And this would be our slope. Okay, so in other words, at the point x equals negative 2, this is the equation of the tangent line. And once we have that in place, we can easily approximate what would happen to this function if there are small changes in x. Okay, so, okay, where would we be? Right about here. Well, all right. Anyway, I guess I shouldn't try to draw it. It's going to be tricky, but anyway, so now with this in place, now if we want to know what happens at another point, we can certainly do that. So actually, you know what, let's skip ahead here and look at 3. Let's start with point 3, x equals 3. And same function, x equals 3, which would be right about here. And this would be our tangent. So the original point 3, the function's value is 0.25. Okay, in other words, if you go back to this graph, okay, oh no, this is the tangent line, sorry. But the point itself is f3 and f of 3 is right here. This is our tangent line. So in order to derive the equation of the tangent line, we go through the same steps. It's the same function. So we have 1 minus 1/4 x. All right, so at point 3, the tangent line f of 3 is 0.25. Actually, I'm not drawing this very well at all. Let me try that again. Okay, let's, oh my God. It's really hard to do this unless you have a large graph. Let me try that again. Anyway, so all right, it's still very difficult to see it, but what I'm trying to show is that at x equals 3, the approximation from this tangent line is 0.25. The actual value of the function is 0.33. Okay, so it's off a little bit. So the advantage of this approach is that it's straightforward, it's easy, especially the function itself is very complicated, but the problem is if you get too far away from the original value, then you're going to wind up with a larger approximation error. All right, well, anyway, so let me go back and grab that original equation for you so you can see what's coming next. Okay, so what this is suggesting is that the equation of the tangent line is approximately equal to the value of the function at that point. Now, here we're using the symbol approximately equal to. To remind ourselves that this is not exactly correct because what's on the right-hand side is the tangent line, the left-hand side is the actual value of the function. So what they're doing here is they're introducing this concept that's very similar to this. Let me copy this so you can see how they're similar to each other. It's in the book, they call this the linearization of f of x near a. Okay, so you notice how here this is using the approximation symbol. Okay, but here L of x is defined as the right-hand side of this equation. In other words, this is the tangent line. So we know that this is approximately equal to the function at that point A, but this is, they're going to call this the linearization. Just a reminder that the tangent line is a straight line. So here's an example of this. Let's say that this is our function. Now, f of x equals radical x looks something like this. So at 9, we know that the function will have a value of 3. Now, here's the thing. What about 9.1? We can use this linearization to come up with at least an approximation, a good approximation to the correct value of the function. So what we're going to do is use the linearization to come up with the approximation, and then we'll compare it to the real value, and we'll see just how close it really is. So you notice that the change in x is quite small. So that tells me that the approximation should be reasonably close. All right, so there's a graph that came from Simulab. Now, of course, in order to do this, we do need the first derivative of this function. Since the function is radical x, remember that's the same thing as x to the 1/2 power, and then based on the power rule, it's just 1/2 x, and here we have 1/2 minus 1, and that becomes 1/2 x to the minus 1/2. Or again, if you prefer, it's 1/2 radical x. Okay, so then we'll need that to come up with our linear approximation. And so we'll solve for this or evaluate it when a equals or x equals 9. Okay, so this is the value of the slope of the tangent line when x equals 9. You can kind of see that here. I mean, it's pretty flat. It's probably better to use the actual Symbolab drawing for this, but you can kind of you see how flat it is. It's only 1/6. Now, what we still want to do, though, is come up with the approximate value of the function when x equals 9.1. Given that it's at 9 right now, what is it going to be if x goes up to 9.1? All right, well, here's the equation. So we already have everything we need. F of x is radical x, f prime of x, as we saw, is 1/2 radical x. Therefore, f of 9 is 3, f prime of 9 is 1/6. All right, so let's plug them in. Oh, and one more thing, remember, a is 9, because that's where we started. So that actually is the equation of the tangent line. It's not written necessarily in this form, or at least it could be cleaned up a little, but that is the equation of the tangent line. And in fact, if you do that, you'll get, just rearranging it a little bit, you get 3/2 plus 1/6 of x. So what this now is what they mean in the book by the linearization function. And in order to approximate the value of the function at 9.1, it's going to be approximately equal to this linearization function evaluated where x equals 9.1. Whatever that number is it's what you're going to get by using the tangent line to estimate the function at 9.1. All right, so when you plug that in, you can see that it is about 3.01667. Okay, so that's the value you'll get by using that tangent line. Okay, now what is the real value of the function when x equals 9.1? That's the interesting question. How far off is this? Well, it turns out to be approximately 3.01662. So the difference is quite small, 0.00005. Now, depending on what you're trying to do, that might be plenty close enough. Like I was talking about with the bonds before, since bonds are priced in dollars and cents, you realistically only need to be accurate within a penny. Anything more than that is really overkill. So that's why it's such a popular technique in the bond markets, because we only really need to be accurate within a penny. And the thing is about the bond pricing function, and this is, again, another reason why we like this technique so much, because this function is extremely difficult to estimate in practice. In other words, it's very rare that you have an actual equation where we know every single point in that curve. So it helps that there's a technique we can use that lets us estimate what these values should be. All right, we could do it, but it would be, this is just, think of it as a quick and easy way of estimating what might happen to the price of your bond if the interest rate changes, given that it only has to be accurate within a penny. Whereas here, we don't know if this is accurate enough. It depends on what it is. Like if you're measuring, this has something to do with, molecules, then maybe this is not accurate enough. But for many applications, this is probably close enough. Anyway, the book has a really nice picture of it. It's easy, they have professional artists doing this. So you can see that this is f of x is radical x. The actual point is right there for 3,9, or 9,3 rather. And then when you move up to a different value, see here, the red and the blue are so close to each other, you really can't even see the difference, because it is very trivial. See here, this one is a bit of an exaggeration, I guess. But the idea is that that the red is the actual value and the blue is only an approximation. All right. Well, now we're going to take a look. Now, you've seen this notation throughout the course so far, this dy dx. Now, it turns out that this is Leibniz's way of expressing derivatives. He came up with this idea. Newton used a different technique or a different notation. And, much of the notation that we use is actually taken from Leibniz. Some people think that Newton may have been first, but it's just that we never found out about it. And so they pretty much both developed the concepts of calculus at roughly the same time. And so they're kind of given joint credit for it. But the one thing that Leibniz did have going for him was that the notation that he used was probably a little bit more straightforward. And so that's what mathematicians chose to use. And that's why we're so familiar with it. It's kind of like, there's probably been other times in history when people developed similar things at the same time. I can't think of any examples off the top of my head, like maybe Tesla and Edison came up with, supposedly a lot of the things that Edison is credited with were actually invented by Nikola Tesla, but he was not interested in money. He loved to do science for its own sake, so he never really patented anything that he invented. And so it's possible that Tesla did invent a lot of these things first, but we just don't know. So, it happens sometimes, and, multiple people come up with similar ideas at the same time. But anyway, so we're going to use this notion of dy dx, but the dy and the dx are referred to as differentials. And you can kind of think of a differential as being an incredibly small change in a variable. In fact, you can think of as a limit. As the delta y keeps getting smaller and smaller, it converges to what we call dy. Dy is the differential. Think of it as an instantaneous change in y. And the same thing holds for x. So in other words, you can think of it as basically the limiting case of delta y. The delta y can be fairly large. It just means that it's a change. Like if you pick any 2 points on a straight line, you can find the slope as delta y over delta x. The points can be as far apart as you want, and we'll still get the correct answer. But when we're dealing with other types of functions, that's not enough. The differential is a tiny difference between x or y, as the case may be. And so for many applications, we use the differential rather than the deltas. Anyway, but the point of it is that because of the way they're related to each other, we have a small change in x, and I mean a very small change in x, triggers a small change in y. So essentially what you're capturing with the derivative is what happens to y when there's an infinitesimally small change in x. That's really what you're trying to capture. Anyway, so we can now go back now and revisit this linearization idea and rewrite it in terms of differentials. And, you'll see that in the diagram, it looks very complicated, but it really isn't, because it captures the idea that when we have very small changes, what we're dealing with here is actually differentials. So this is the linearization function we saw earlier. Now, what they've done here is they've said, well, listen, what happens if instead of being at point x, we're at a plus dx? In other words, a is some starting point, and then we have a tiny little change in x. So since f of x is approximately equal to L of x, it means that f of any function or any value, like here we have a plus delta x, dx, must be approximately equal to L of a plus dx. Now, so what we're going to have to do here on the right-hand side of this equation is, if you notice, the x minus a has been replaced by a plus dx minus a. Okay, so in other words, all the x's are replaced with a plus dx. And so what that leads to is this. And again, it should make more sense when you see the diagram. Assume that x increases from a to a plus dx, a tiny, tiny change. The increase in f can be approximated by L, which is the point on the tangent line, minus f of a, which is the original starting value. All right, so let's look at the graph and see what this is all about. So again, it looks terrifying at first, but let's start at the horizontal axis. Here's the starting point. We have a, some constant. Here's a, f of a. Okay, so this is the point a comma f of a. Then we increase x by a tiny, tiny, tiny amount. So the question is, what happens to y? Well, if we use our linearization function, we end up with a plus dx comma. Now remember, this is the x coordinate. This is where x is now. The y coordinate is approximately equal to L of a plus dx. The actual new value is a plus dx comma f of a plus dx. So the approximation error is the difference between the two. Which should be very small, which is why we said before that these two are approximately equal to each other. And so according to the linear function, the change in y can be written like this. In other words, dx is the vertical distance, horizontal distance here. And then f prime of a is where we started here. So in other words, they're doing this with geometry. Okay, this is the rise, and this is the run. Okay, so when x changes by dx, according to this linearization function, dy changes by f prime of a times dx. But the actual change is here. That's what the function is equal to at that point. So anyway, so we can figure out, but you can see that the two are very close to each other as long as dx is very small. And of course, by definition, dx is an infinitesimally small change. So therefore, the result must be very accurate. All right. So let's just look at one very quick example of this. Suppose we have the function y equals x squared plus 2x. We need to know dy, which remember is the change along the linearization function, and determine its value when x equals 3 and dx equals 0.1. So actually, let's take a look at Symbolab and see what this thing looks like. Where is that? Okay, here we go. X squared plus 2x. All right. Okay, it's just a standard parabola. Now, the point, oh boy, look at this. We need x equals 3. Wow, that's, geez, it's going to be huge. 15. That's why, yeah. That's what the problem is. So we've got to really shrink it up here. When X is 3, Y is 15. So what we're, okay, well, let's try to draw this. Oh, okay. Well, yeah, you can see this one is really tough to draw. Hold on. No, that's okay. So at 3.1, we have the actual function this is f of 3.1. Okay. And then we have the approximation. Okay. So the approximation, so the actual function itself will be f of 3.1. The approximation will be a plus dx, which we know is 3.1. And then we'll have L of a plus dx. Okay, the actual value here, we could write it as a plus dx comma f of a plus dx. In this case, a is 3, dx is 0.1. So obviously a plus dx is 3.1. And based on the function being x squared plus 2x, we already saw that f of 3 is 15. So f of 3.1, I think I calculated down here below, it is 15.81. That's the actual function value. But as far as the approximation goes, we have, let me just copy it here. So L of 3.1 so it's going to be f of a. The derivative, f prime of x, is 2x plus 2. So that f prime of a is 8. Okay. And then, since x is 3, let's see. Oh, wait a minute. No, this is not right. sorry, this is supposed to be L of A plus dx here it is. This is what I needed. Hold on one second. We need L of A plus dx here. Okay, so remember 3.1 is A plus dx. So f of A is the 15 plus f prime of A is the derivative when x equals 3. That's the 8. And then the dx is 0.1 by assumption. We chose that we actually choose that ourselves. So you've got 15.8 as your approximation from the tangent line. The actual value is 15.81. So at least in this particular case, it worked out quite well, as a matter of fact. All right, so there's our approximation. And this is the actual function value. Okay, now we're good. All right, so I'll just pencil these in over here. 15.8 and 15.81. Okay, now we're good. Wow, that was a lot of work, wasn't it? Yes. But the idea here is just once you get used to this linear function, you need to know the original f of A. You need to know the derivative, because remember, that's giving us the slope of this tangent line. And then that's being adjusted by the size of the change, dx, so that in other words, we're moving up to a different point on the same tangent line. And so that's where this is coming from. The same starting point, 15, but then we're moving up the tangent line to a different position. And we're using the slope of the tangent line, f prime of A, and the width of this dx to come up with a new point on the tangent line, which in this case is 15.8, as opposed to the actual value of 15.81. So the more curved the function is, the worse the approximation will be. Now, this one, you saw that even though it's a parabola, it's a very steep parabola. So for a very large number of x's, these two, the function and the straight line, are not that far off from each other. So in this case, it worked out rather well. There are going to be other functions where this doesn't work so well. If the function itself is highly nonlinear, then you can't really expect this technique to work all that well. But here it did, because like I said, if you look at the shape of this function, it's really steep. And so that makes it behave more like a straight line. But anyway, so with all this being done, now this next section, this is basically our first introduction to optimization techniques. This is a huge, huge, huge area of study. A lot of the applications of calculus are really designed to help us maximize or minimize functions. Classic example would be in economics. We might want to know, for example, the maximum profit that we can earn given the functions for our costs and our revenues. We also may want to know what minimizes the cost of production. And so you can imagine there's a lot of different applications where the idea is to figure out maybe the best place to produce your product. How many units should we produce to maximize our profits? Or possibly how many should we produce to minimize the expenses of producing it? And then it's not just, of course, economics. So many other disciplines also, you will find it necessary to optimize a function by finding either the maximum or the minimum values. So it turns out all this can be done with derivatives. There's more than one way of doing this, but remember, since a derivative is a rate of change, imagine that you're trying to figure out how to maximize your profits. if I discover that increasing my output reduces my profits, that means obviously I'm making a terrible mistake. So it's that rate of change that helps me make sure that I'm choosing the right point to produce at. So anyway, we have to be very careful with the language here. These are Latin words, and so the pluralization is maybe not what you were expecting. The word maximum, everybody knows, and the word minimum, but it turns out that the plural of maximum is maxima, and the plural of minimum is minima. Now, a function can have many different points at which it reaches a minimum or a maximum, and there's two basic types of minima and maxima. Let me just show you a quick couple of graphs. Let's try something like this. This is some weird function, and you can see that what happens is it reaches these little peaks and these little valleys, I guess you could call them. And so what we would say here is that within a fairly small range of, let's call this x1. This is the largest value the function can attain within the immediate vicinity of this x1. In math, this would be called a neighborhood. In the immediate neighborhood of x1, there is no other point where the value of the function is larger. So this is often referred to as a local maximum, in the sense that there might be other maximum points, but within this area, this is the maximum point. This one, based on that same logic, would be referred to as a local minimum. This one is also a local maximum, even though this one is higher than this point here. This is x1 comma f of x1. This is x3 comma f of x3. So even though f of x3 is greater than f of x1, this one on the left here is still considered to be a local maximum, because again, within that region, there are no other points at which the function is greater. So we have two, in this case, local maxima. Now I'm assuming, by the way this thing is drawn, that from this point on, it just goes down forever. And here I'm assuming that it's just same thing. Okay, so notice we're not seeing the entire function, but we're assuming that outside of this range, it just continues to rise from the left. And then after we get to x3, it just continues to fall forever. So these are called local maxima and local minima. Now, by the way, I just want to give you a sort of a hint. How do we find these points besides looking at the graph? It turns out that if I were to calculate the derivative of this function at these points, f prime of x1, for example, the slope of this derivative is equal to the slope of a tangent line at that point. And you can see the slope of that line is 0. Okay, in other words, having a slope of 0, a derivative of 0, sorry, means that the tangent line has a slope of 0, which means it's flat. Okay, same thing for x2. You can see a tangent line at that point is flat. It has a slope of 0. And then once again, we have the same thing. So that's what these points have in common. All right. Now, it's not always the case that a slope of 0 leads to a maximum or a minimum, but if it is a maximum or a minimum, it will have a slope of 0. So that makes it easier for us to identify these points. And this is what we're aiming for. Like if, again, if this represented a profit function, obviously I'm not going to include anything outside of the first quadrant, but in this graph that I've drawn, if this is a profit function, then I want to produce at x3. Okay, now a maximum or minimum, these are both collectively an extreme. All right, let's put it this way. The word extremum is either a maximum or a minimum. Okay, so in other words, a maximum or a minimum are both specific types of extrema. All right, so let's get this straight right now. A maximum is an extremum, and a minimum is an extremum. Actually, oh, whoops. They're both examples. Those are the two types of extrema that you can run into, a maximum or a minimum. So the word extrema includes all the maxima and minima that your function has. Okay, in other words, in this example, I had 3 extrema on my graph. 2 of them were maxima, and 1 of them was a minimum. So yeah, and so because these are only within a certain range. Now, actually, I had another graph already drawn here. You can see this, it's the same idea. You've got 1 local maximum and 1 local minimum, and these are both collectively known as extrema. Okay, and again, you can see that they have a flat tangent line at those points. Now, what we're going to look at here is the formal, and I mean formal definition of what it means to be a local maximum and a local minimum. In math, we need to be extremely precise and rigorous with our definitions. And, in a more advanced course, you might be asked to prove some of these results. So, down the road, when you get further ahead, you'll see that, I mean, even in this book, the proofs are there if you want to look at them, but they won't ask you to do any of them until you really get further along, like let's say at least into Calc 3. And once you get into a more advanced class, like Calc 4, as it's called at some schools, or some schools call it like real analysis, that's all you do basically is proofs. That's when you're really getting deadly serious about math, because a lot of it is simply based on proofs. Now, if you're more interested in the applications of math, then you might want to study a more applied area like physics or economics or something. But math itself, pure mathematicians do spend an awful lot of time with proofs and developing results. So here we go. So the language may seem a little challenging, but a local maximum means that f of x has a local maximum at x equals point C if there exists an open interval. Now, the words open interval means that it does not include A or B. The round parentheses, I guess we'll call them, indicate that this does not include A or B. It's everything in between. The opposite of this would be a closed interval. It would be written like this. And the square brackets indicate that it includes both A and B. Okay, so that's an important distinction, all right? Because what will happen here is that some of the properties we'll see are only true over an open interval, and sometimes it's only true over a closed interval. If one of the endpoints here is infinity, we don't use the square brackets for infinity. Okay, we always use the round parentheses. Anyway, if we have an interval over our function, which means we're not looking at the entire function, we might be looking at, let's say, just this piece here. The interval, now, of course, also keep in mind, the interval has to be in the domain. You can't have, this isn't going to work if you've got like a gap in your function. Okay, so as long as I is contained in the domain, if we discover that f of c is greater than f of x for all the x's. So let me see if I can draw that. Let's try that again. Okay, this is pretty good. So the idea here is that this is f of c right here. Okay, this is c, this is f of c. All the other points, no matter what, let's say this is x1, this would be f of x1. They're all smaller than f of c. So that means this is my local maximum, because there's no other points within that interval where the function has a greater value of y. So it's just a more formal way of saying that if you look at the graph, you'll see that it peaks out, so to speak, at that point. Okay, and if you notice that, again, it has to be defined with respect to an interval because there can be more than one local maximum. Now, the local minimum is just, everything is exactly the same. The only thing that got changed is right here. Okay, so that you're looking at something like this now. So in other words, no matter where you look in here, f of c is the smallest value of the function in that interval. That's what this is telling me. Okay, so yeah, the optimization is a very, very important, but I think it's extremely interesting too, because it works great, but sometimes you can run into these very bizarre situations. So that's why you need to have all these formal definitions. And sometimes you can find functions that actually do not have either a maximum or a minimum. It does happen. So there's no guarantee that a function will have either one of them, but most functions have at least one of each. But again, it's not guaranteed. All right. Anyway, so before you carry on with this stuff, I think we'll stop and have our break right now. And when we get back, we'll dive more deeply into this concept of maxima and minima. And then when we are finished with the local minima and maxima, we'll see that we also have something called a global or absolute maximum or minimum, which represents the largest value in the entire function, not just in an interval, but in the entire function. Okay. All right, so we'll stop here. When we come back in about 15 minutes or so, we'll take a look at some more concepts here. All right. All right, we're back. So now here's another definition. A point that is inside of an interval. Let's say, for example, we are here. C is some point. Basically, it could be, when you come right down to it, it could be anywhere in the domain, or sometimes it refers to a point inside of an interval. It just has to be in that range somewhere. In other words, we can't have it to be, let's say, infinity or something like that. It turns out that if at that point we have one of two things, let's say we have a derivative of 0, meaning that the tangent line is flat, or possibly if we have something like this going on, at this point, f prime of C is undefined. Okay, either way, that C is known as a critical point. All right, so now some critical points represent a maximum or a minimum, some do not. Some of them simply represent points where the derivative is undefined. So we have to be careful with that, but what will end up happening is that when we're trying to maximize or minimize a function, what we're essentially doing is looking for critical points and then testing them to see if they're either a maximum or a minimum, or possibly a point where the derivative is undefined. Now, if, on the other hand, if we work this backwards, once we discover that this is let's say a maximum, that ensures that C is a critical point. So in other words, if we know that this is a maximum or a minimum, that guarantees that C is a critical point. All right, now we're going to see this very interesting result, Fermat's theorem. Now, Pierre de Fermat was a very, very famous mathematician. I forgot what century. I think we're looking at the 18th century, but let's double check him. One of the reasons why he's so interesting is because there's one of his theorems. First, let's look him up. And so we're looking at, even further back than I realized, we're looking at the 17th century here. And of course, he's one of the really, all-time great mathematicians, but there was a theorem that he developed. And apparently in one of the books that was found in his library, he had written with a pencil, he'd written into the margins, I have found a wonderful proof of this, or something to that effect, and nobody could find the proof. And so it took literally centuries for somebody to come up with that proof that he supposedly discovered. There's actually a book written about this. This might be the one. It's called Fermat's last theorem. His conjecture states that no three positive integers a, b, and c satisfy the equation a to the n plus b to the n equals c to the n for any integer value of n greater than 2. But this is the one, I believe, that nobody could find the proof of. There it is. This is it. The proposition was first stated as a theorem by Pierre de Fermat around 1637 in the margin of a copy of Arithmetica. He added that he had a proof that was too large to fit in the margin. So, but if he wrote it down somewhere else, it was lost. Okay, nobody was ever able to find it. Eventually, yeah, there it is. They finally were able to prove it in 1994. Okay, Yeah, I mean, we're looking at from 1637 to 1994 it took to find that proof. Wow. So this guy is a big deal, of course. But Fermat's theorem was like one of these challenges to all mathematicians to see if they can come up with that proof. And so finally somebody got to it. And according to that, Guinness Book of World Records called that the most difficult mathematical problem. Interesting. But anyway, that's one of the things that Fermat is known for that last theorem that nobody could prove for 350 years, even though he supposedly did. Nobody will ever know because whatever he wrote was ultimately lost. Anyway, but here, this is a much simpler idea. All he's saying is that if a function has a local extremum at x equals c, and if it is differentiable at c, then its derivative must be 0. Okay, so as long as we see that this is an extremum, and of course it's differentiable at that point, then it must have a slope of 0. Or in other words, this tangent line is flat. But it doesn't always work both ways, though. In other words, you could actually have a function where the derivative is 0 and yet it not be a maximum or a minimum. Now, it's hard to draw those examples. There's one here, two of them actually, that are very tricky. If you look here, obviously this one does have a local maximum. F prime of c is 0. This one is interesting because this function technically has a local maximum, but f prime of c is undefined. And then the same thing's here. Now, derivatives are always undefined when there's a sharp break in the function, because what's happening is that you're converging to that point from opposite directions. And so when the point of a derivative is that it has to be smooth and continuous, and that as we get closer and closer from either direction, we're getting closer to the same value. And here that isn't happening. Okay, whenever there's a sharp break like that, or sharp point, that means that the derivative is undefined. And so yet at the same time, though, we still have a maximum or a minimum. So these are still defined as critical points, because f prime of c has to be either 0 or undefined. So these all qualify as critical points. Now down here, though, now here's an interesting graph. Now it's kind of small. It's kind of hard to see it. Let me see if I can draw it a little bigger. There's a point in here somewhere where, oh my God, let me see. Oh, I didn't draw it very well at all. But there's a point somewhere in there, if you draw this correctly, where you do in fact have a flat tangent line. Let's say right about here. So f prime of c is 0 here. And yet the tricky part here is that in spite of this, so even though f prime of c is 0 and c is therefore a critical value or critical point, there's no local extremum or extremum. Okay, so in other words, what this shows us is that it's possible to have a derivative of 0 there and yet not have an extremum. Okay, because what's happening is the function is essentially changing directions. You can think of it as you're increasing at a decreasing rate and up to that point, and then all of a sudden you start increasing at an increasing rate. And so while the slope is flat at that one point, you still do not have an extremum. And then there's another way this can happen. And again, it's very tricky to draw this type of diagram, but you can see what's happening is that the f prime of c is not 0, but it's actually undefined because that is a vertical line, and therefore the slope is undefined. So the critical values, these are all critical values, but in only the first 3 cases do we have a local extremum. In the second 2 cases, in spite of the fact that the C is a critical point, we do not have a local extremum. All right, now, most of the time, what we're going to try to do in these cases is we're going to take a function and try to figure out where the local extrema are, if they exist. Okay, so we either want to find out where they are, if they exist, or if they don't exist. So what we're going to do here, and by the way, this is something that can be done in many different ways. We're going to start with a very basic approach. We're going to start by taking the derivative and setting it equal to 0. Okay. Actually, this should say f prime. We want to know where the first derivative is equal to 0. Okay, so that'll be pretty straightforward. So, for example, here, here's our function. And by the way, let me go get Symbolab and see what this thing looks like. Okay, where is it? Nope, that's not it. That's right. I'll open up a new copy of it. Oh, wait, what did I do? X cubed. Oh, sorry, 1/3 x cubed. Minus 5/2 x squared plus 4x. All right, let's take a look at this thing. And when you look at the graph, you'll see, oh, well, I think it couldn't be more obvious where the local maximum and local minimum are, but we have to formally prove this. Okay, we can't just say, well, look at the graph, there they are. No, it doesn't work that way. All right, let's sneak that in there so we can use that as a guide. Oh, but it's hard to see with the labeling, but it looks like we have see, this is why the graph isn't really good enough, because you can see that here x is 1. The y is almost 2, not quite. And then here the x is 4. The y is it's very close to -4, it looks like. But it's hard to be positive with a graph. That's why we need to do this algebraically. So here, let's do it. But this is what we're looking for. Clearly, this is meant to be a local maximum, and this is a local minimum. All right, so where do we find them? Okay, so first let's take the first derivative. Now, using the power rule, you can see, for example, for 1/3 x cubed, f prime of x would be 3 times 1/3 x to the 3 minus 1. Okay, that would be here for -5x. Now here, remember, there's an implied exponent of 1. So what we actually have here is 1 times -5, x to the 1 minus 1, or you just end up with -5. Oh, sorry, it's 2. I copied it wrong. It's 5x squared. Here we go. Let me try that again. I obviously copied it wrong. I was looking at this one instead of this one. -5/2 x squared. Yeah, now we're getting somewhere. So it'll be 2 minus 5/2 x to the 2 minus 1. So this works out to be -5x. And of course, this one is just 4. Now, for something like this, since it's a quadratic equation, you can use the quadratic formula, but here it turns out that factoring it is very, very simple. And you can still feel free, go ahead, use the quadratic formula if you like, but it turns out that we can break this down into x minus 4 times x minus 1, which you can double check with FOIL. And when we set those individually equal to 0, we have the two critical points, 4 and 1. And that's what we saw in the graph. We already knew that the points were 4 and 1. The question is, what are the values of y at those points? So that's a simple matter of plugging them into the original function, which, let me just remind you, is right here. And so f of 4, you literally just replace all the x's with 4s, and you can see it's -8/3. Okay, so that is hard to see on a graph. -8/3, all right, I guess we'll have to take their word for it. Yeah, you can see why, because the -3 is right here. The -2 is here. So it's 2/3 of the way between -2 and -3. So that looks right. And then when we do the same thing with 1, we'll end up with 11/6. So it's just a hair under 2. And again, you can see we didn't quite reach 2, but it's close. So this is the point, 1 comma 11/6. And this is for -8/3. So those are the two extrema. Okay, now, how do we know which is which? Because the value of f of x is, well, clearly it's positive for x equals 1 and negative for x equals 4. But there's a more formal way we can tell them apart. In other words, what we're applying here is sometimes known as the first derivative test. And the first derivative test, let me just sneak this in here because we'll be doing this very soon. The first derivative test enables us to find the relative or local extrema, determining whether they are maxima or minima can be accomplished in at least 3 different ways. One of these, which we'll see, in the near future, is the second derivative test. In other words, it turns out that if we examine the sign of the second derivative, that will uniquely identify whether each of these points is a maximum or a minimum. The first derivative test can only tell us if these are extrema. It doesn't tell us which is which. Here we're relying on the graph to do that. Okay, so you can see very clearly that when x is 1, we've reached a relative maximum, or local maximum. And when x is 4, we've reached a local or relative minimum. But if we didn't have the graph, we would not be able to tell which is which unless we apply the second derivative test, which we'll get to probably later in this chapter. There's another approach too, where what happens is, given that this is a critical point right here, what we can do is look at the sign of the function, the derivative rather, on either side. In other words, here, just as we're reaching x equals 1, the first derivative is positive. Here, it's negative. Down here, just as we're approaching 4, first derivative is negative, and here, the first derivative is positive. So it turns out that when we have this experience, when the derivative goes from positive to 0, which it is right here, and then to negative, that ensures that this is a maximum. And down here, when the first derivative goes from negative to 0, which it is here, to positive, that tells us that this is a minimum. So in other words, you're using not the second derivative, but the first derivative, but you're only interested in the sign on either side of this point to see whether or not it's a minimum or a maximum. So that's another approach that we could use to find out what type of extrema these really are. So, and then don't worry, we'll eventually get to the second derivative of the case. All right, now, I mentioned we've been talking about local minima and maxima, which are only restricted to certain regions within the graph. But it turns out that there's also another type of extrema that we can consider, which is called the global, or sometimes it's called absolute. In fact, let me make a little note here. Because again, like as is often in math, there's multiple words that mean the same thing. An extrema, or extremum, I should say, all right, let's put it this way. A local extremum can also be called a relative extremum. When we find an extremum that applies to the entire function, not just in a small region, it's called a global or absolute extremum. Okay, so in other words, a global extremum, which applies to the entire function, can also be called an absolute extremum. So every textbook is different. Some of them use the terms local and global. Some of them use relative and absolute. Sometimes they use both. I'm more used to calling it local and global, so I'll stick with that. But the book, I believe, just typically is referring to these as absolute. But it does mean the same thing. So let me show you an example of what this is all about. Look at these two parabolas. And the one on the left, you can see clearly that there is no other point on this function that has a higher value of y. On the right-hand side, it's the opposite. There's no other function or value that falls below this point. So these are known as a global maximum and a global minimum. It doesn't matter. This applies to the entire function. Now, it's not necessarily the case that a function always has either a global maximum or minimum. It doesn't have to. But here, of course, they do. So the difference between this case and the local case is that there can be several local extrema, but can only be one global. Okay, think of the global. Let's put it this way. A function's global maximum can be thought of as the largest of all the local maxima, and a function's global minimum can be thought of as the smallest of all the local minima, of course. Okay, so it's basically that is the largest value that the function can attain over its domain. Okay, so in other words, a local extremum is restricted to an interval, a global extremum applies to the entire domain. Okay. All right. Now, how? Oh, by the way, here's some wild looking graphs. You don't know what some of these functions might do. This is one of the advantages of working in an applied area like economics. You're not going to get all these bizarre functions. You might see them in other disciplines, but not so much in economics, but they do exist. Let's look at these things. Now here, this first one clearly does not have an absolute maximum or an absolute minimum. In fact, it doesn't even have a local maximum or minimum. Because you know why? Because even though there's a critical point here, you can see that it is clearly not a maximum or a minimum. Over here, we do have an absolute maximum or global. But there is no absolute minimum, okay? There doesn't have to be one. Now here, you got, this is a cosine. These are very bizarrely behaved. It just cycles through the same, it goes over and over and over again, repeats the same cycle. So you actually have three, well, within the graph, you have three absolute maxima, and then you have all these absolute minima, and there's an infinite number of them. I mean, this function goes all the way from positive to negative infinity. So this is one of those rare cases where there's actually more than one. They're all basically tied with each other for the largest and smallest possible values. So you've got multiple absolute minima and maxima. Very unusual. Here, now this is an interesting case because you can have an absolute maximum because this function is only defined between 0 and 4. Okay, so within that range, we can say that, well, what do you know? There's an absolute maximum. There's no absolute minimum because the function is undefined at this point. If this was filled in, that would have been the absolute minimum, but because it's not, there's no absolute minimum. Here, the function over this interval, the function never falls below 0. That's our minimum. And it never goes above 4. That's our maximum. Now this one, because there's an asymptote, it's considered to have no absolute maximum, but it does have an absolute minimum. Okay, so yeah, you can see you're potentially going to run into some of these very strange cases, but for well-behaved functions like parabolas and that type of thing, you should have no difficulty whatsoever identifying the absolute and relative minima and maxima if they exist. All right, now there's a theorem here, and basically what it's telling us is that if we have a function that's continuous over a closed interval, and that means, say, from one, actually, let's look back up here for a second. This one has, this is defined over a closed interval. It starts at 0, including 0, and it goes up to 4, including 4. Actually, yeah, this one on the far right, by the way, here's the thing you've got to pay attention to. If you notice that this one is defined from 0 up to, but not including 2. So what this theorem is essentially saying is that if the function is defined over, if it's continuous and defined over a closed interval, then we're guaranteed that somewhere in that interval, we will find a global maximum, and a global minimum. Okay. As long as it's defined and it's continuous. Now, you see here, for example, the function fails because it is discontinuous. So that means the extreme value theory fails to hold. But in the second case, we have both. And that's because the function is defined over 1 to 4. And it's continuous throughout the entire function. And that means we have to find it, of course, but we are guaranteed that they both exist. The global maximum or absolute maximum and the global or absolute minimum. Here we have a problem right there. It is not defined over a closed interval. Okay, sometimes this is called semi-closed. Sometimes it's called semi-open, but the bottom line is that it's not completely closed. It does not include the two. And for that reason, we cannot guarantee that there's both an absolute maximum and minimum. And in fact, you can see there isn't an absolute maximum. So in this case, the extreme value theorem is saying, well, you've got a function that's continuous over a closed interval. Therefore, there must be both a global maximum and a global minimum. Now, it's up to you to go find it. All right, now that's kind of potentially very helpful if we have weird, bizarre functions. We don't want to waste our time looking for a maximum that doesn't exist. Now, how do we find these? We've already seen one technique for finding local minima and maxima, and it involved the first derivative, setting it equal to 0. What are we doing here, though? All right, well, because here we're looking at closed intervals, the extreme value theorem and Fermat's theorem are going to jointly tell us that if the extreme value theorem holds, and which means it's guaranteed to have a maximum or a minimum, if that extremum does not occur at the endpoint, it must occur in the interval, in the interior, that is. And if that's the case, the global extremum is also a local extremum. Now, all of that is telling us this. If you look at this function right here, the one in the middle, we know that the extreme value theorem holds because the function is continuous throughout this closed interval from 1 to 4. It therefore has a global maximum and minimum. But if you notice, the global minimum does not occur at an endpoint. This one does. Okay, so this global max, because it occurs at the endpoint 4, is also a local max. Sorry, I got that one backwards. Hold on one second. No, it's the other one. This is not a local max, but this one is. Okay, unfortunately, I said that backwards. This one, because it occurs in the interior, in addition to being a global, we define it as a local max as well. Local minimum. It's both. Okay, because it occurs in the interior, if it's a global minimum, it is also a local. Okay. So anyway, how do we find these? All right, here's what we're going to do. Given the interval AB, we're going to calculate the value of the function at those 2 points. And then we'll look at the interior, which means all the points between A and B, not including A and B, and we'll identify all the critical points in the way we did earlier. In other words, by setting the derivative equal to 0 and solving. Okay. So, all right, let's look at an example of this. We've got this function, and we're only interested in the area between 1 and 3. Now, I looked at Symbolab, and I looked very hard. And while it certainly can graph this function, I was unable to find a way to restrict the graph over the interval 1, 3. So I think what we should do is just see what this thing looks like. And then focus our attention on that range between 1 and 3, or that interval. So it's negative x squared plus 3x minus 2. So this is what the graph looks like. Oh, that's interesting. It just barely peaks over the top. Oh, here we go. All right, so let's grab a copy of this. So the area that we're interested in is the range, the interval 1 to 3. Okay. So let's see if we can approximate where these points are. So 1 would be, it looks like it's about here. And then the 3 is right about here. I don't know if I've drawn that well or not, but I could try again later on. I'll look at the instructions again and see. But so anyway, so what we're going to do is figure out the value of the function here. And so now, see, this is a little confusing in the way they've done this. Oh, maybe not. This is meant to be the 0. Okay, it's hard to tell sometimes with this graph. So in other words, this is the horizontal axis right here. So that means this one is easy. This is just 1, 0. And then this one, well, it looks like it's supposed to be 3, -2. So we're only interested in this region here. So anyways, if you actually go ahead and plug in these values into the function, yeah, there it is. It did work out that way. So the 2 points of interest are 0, 1, rather 1, 0. And 3, -2. Those two potentially could be global extrema. They don't have to be, but they might be. Think of them as candidates. They're possibilities. Now, if you look at the picture, you can see that clearly neither one of them is a global maximum. But this 3, -2 appears to be a global minimum. So what we need to do now is take this function and figure out where there might be any critical points in the interior of this interval. And it looks like this is the point that we want, because clearly the tangent line here has a slope of 0. So how do we identify this point? Well, we'll go to our function, take the first derivative, set it equal to 0, and there it is. X is 3/2. Okay, so let's go back to our graph. Now, I guess that looks about right. 3/2. So what is the value here of the function? Well, we just plug that in. And that turns out to be 1/4. Okay, so once again, the points of interest are 1, 0, 3, -2, 3/2, 1/4. Now, because this function is continuous over a closed interval, we're guaranteed that one of these is a global minimum and one of them is a global maximum. Okay, so the question is which is which? Well, I think from the graph, it's pretty clear that we have a couple of winners here. This is our global maximum. The point 3/2, 1/4. And this would be our global minimum. Okay. So there we are. So we're done with it. Okay, well, that seems like a lot, but it's more straightforward than it seems. I mean, ultimately, most of the time, what we're just going to basically be doing is taking the first derivative, setting it equal to 0, finding the critical points, and then solving for them. And then we have to apply one of the tests. We can look at the graph, we can look at the first derivative signs, we can look at the second derivative. That will help us identify relative maxima and relative minima. But for the globals, we need to go through these extra steps. We have to look at the endpoints, and then we look at the critical points to ultimately identify where we have global extrema. All right, so I guess that's going to have to do for today. Now, next week, when the first recording, I guess, what I would like to do is go over the sample midterm, which I'm still finishing up, by the way. And so think of it as just a bunch of practice problems that are going to be very similar to what the actual midterm looks like. So you'll be able to follow along and see what the answers are. And you'll know right away if you understand or not. So we'll do that next week. And when that's done, we'll move, of course, further into chapter 4 because we have a lot more ground to cover. In fact, I remember there's a list up here of all the topics that we're doing. And so we're going to, actually, we're going to revisit limits again. We're going to look at some more complicated limits. Newton's method is a very interesting idea. Well, what you're essentially doing there is you're looking for the solution to a function that can't be solved directly. So you'll see what that means when we get there. And then antiderivatives is a very interesting idea. You're essentially reversing the process of differentiation. But we'll get to those in good time. Okay, so in the meantime, we'll just knock it off right here. And so if you haven't already done the second problem set, you can hand that in tonight. You can start working on the third one for next Thursday. And in the meantime, I'll let you know by email when the recordings are ready, or you can just look at YouTube. And like I said, you can feel free to watch them in your spare time. You don't have to watch them, in our normal time. And it'll be the same thing that we're used to seeing, except that it'll not be in real time. And then next week, we'll be back to normal. Okay. And even though I'll be away, you can still always reach me by email if you have any questions of any kind. So, all right. So if you don't have any questions now, I guess we'll stop here. And you'll see the material next week, but I'll see you in a week from Monday. Okay.
Thanks, Professor. Have a good night.
Thank you.
Good night.
Thank you.
Bye.